Good evening, everyone. Welcome to the final session of Operating System Fundamentals live interactive session. So, in the previous class, we have looked at the concept of this scheduling and a couple of problems on that, which was discussed in week 12. The topic that was left was file system. So, we'll quickly go through one or two numericals from file system accessing, and then in the rest of the session, we'll take a look at different problems from various topics that we have dealt till now, like CPU scheduling, paging, synchronization, disk scheduling, etc. We'll go through some of the numericals from there. So typically in the last class, the discussion started with a file. What is a file? What are the attributes a file has, and the various operations that we do on a file. So typically, a file is nothing but uh, to say an entity where we store data or content. So typically to identify a file, operating system have something called as name, identifies type, the size, its location where it is present and all that. And the operations that are allowed on files are normally create, write, read, delete, etc. So a file can be of different type. One of the simplest one is like it's a sequence of bytes. So either a file can be of sequence of bytes, or it can be of fixed size records, or it can be of variable size records as well. And these files, one can access the files either sequentially, that is byte by byte, or we can directly jump to a particular location, a particular record, and then access that is direct access method. So, in a sequential access, typically we access the file one by one. So, whereas in a direct access, it is directly we go to the particular record that we want to access. It's comparatively, it's faster actually. Then and another concept discussed was a directory. Directory structure is used to organize the files in the operating system. So we can have, give me a minute. So typically we can have directory structure can be of a single level directory or a multi-level directory. In single level directory, it implies that there will be a directory will be there, and from each directory, only one more level of where files will be stored. There will not be recursively within a directory. We will not have multiple directories, and within inside which we will go and store. So single level means one top level directly, and inside that all the files will be stored. Whereas in two level, it means yeah, in two level it means one level, and again we can have another one more level of grouping and other things. And the other one is the most commonly used structure is the tree structure. So we can have a number of so all these will be of in Windows terms we call these as folders. Directory or folder, and within the folder this leaf will be a file of any type. So that's about directory, and then we can also have these directories shared between files within one directory, shared in another directory, and those are achieved using what is known as aliasing and all. And then another thing with these files and all are like when we create a file, we can also tell the permissions. We can set the permissions for the file, like who should be able to access it, who should be able to read it, write it, and execute it. So, in typically in Linux, we will have a 1, 2, 3, 4, 5, 6, and 7, 8, 9. So this for every file we will have this many bits. So this set of 3 bits tell the permissions for the owner. The other one tells the if it is part of a group. If a group is allowed to access this file, what are the access given to the group and what are the access given to other public. So if it is all one, it means full access, read, write, and execute. If it is only read, then it will be 100. If it is only write, it will be 010. Or if it is only execute. So based on the privilege or the access rights vary. Okay. So another, and then the next topic is the allocation actually. How are these memory allocated for these files? So there are majorly three ways of for disk allocation. One is continuous allocation, another is linked allocation, and the third one is indexed allocation. So in continuous allocation, so the whole file will be stored in continuous blocks in the disk. Okay. So one problem with here is like we have to. So if a file is of certain size, we need to find continuous blocks of that much size. So. Uh, there is always a possibility of bringing in external fragmentation here, and a later point, if we want to extend the file also, we need to have enough space in that continuous location itself. So that is one problem with continuous allocation. But this is for performance wise, it is always good because like on the disk, if these are the blocks in continuous allocation, if the file starts here, the next set will be here, next will be here, and next it will be on the continuous blocks. So performance would be better, but the problem is, for example, if we had a um, 5 block free and after that all the blocks were occupied, and this file was having occupying this occupied 4 blocks. Now suppose we have some additional data for 2 more blocks. There are no more blocks available, only one is left. So now we need to find a place for all the 5 of this and then move it. So that those are the difficulties. And this in the other another external fragmentation is like we are having this one which is not being used as a whole here, because if all the other files needs more than one block on the disk, then this will not be used at all. So holes gets created. So that is with continuous allocation. With linked allocation, how it happens is it will be like a linked list. So we can the blocks could be scattered across. So from first block, we will have another pointer to the next block. For example, if we have blocks like this on the disk, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and for the file, the starting block is 9 and the end block is given as 12. Then first there will be a link to 9. From 9, it will go to next one. It is 10, where the next, in the next block where the content is stored. Now, if the further file contents are stored on block 1, there will be a link from 10 to 1. Then if the next is stored in 3, then there will be a link from 1 to 3. And then last to 11. So, but one difficulty with this approach is that we will only have the start pointer stored. Okay, so if we want to read something which is there in this particular block, we need to traverse, we need to go to 9, 10, 1, and 3, and then read it. So we need to traverse through the entire block. Whereas in case of contiguous allocation, here, see, we had it in this uh, 4 blocks, and if I knew that this is where the data has to be written, we can directly go here because these are contiguous blocks, right? And you know the size of the block. If you know the offset within a block, one can easily go and read it from that respective block. So that is the disadvantage with link allocation is this one. All the blocks have to be traversed, but the advantage is no external fragmentation, no external fragmentation, and no holes created. So those are the advantage. Another mode is the indexed allocation. In indexed allocation, these are normally used for large file. So here we will have a index. There will be an index file first, which will tell the index where which all blocks are available in this index file. So the initial file reference will have the file name followed by the location where the index file is stored. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it tells that the index file is present in block 19. So this will be first taken and brought. That is this one. Then we know the first block from the disk to be read as 9. That is this one. Then the next one is 16. Then 1 followed by 10. So this is how we will have the index to each of the disk blocks in another file called the index file. So this is how indexing works. Okay. So that's pretty much about our file system. So we'll quickly take a look at one problem. So yeah, so let's consider let's consider two file system A and B, which is having, so A is having contiguous allocation and B is having linked allocation. So we are having a file size of, given a file size of 100 blocks, and it is already stored in A and B. One in a contiguous manner and the other in contiguous manner, this in linked manner. Now, if suppose we want to insert a new block in the middle, insert middle of 50 and 51. Sorry. Now, if you want to insert a new block in the middle of block 50, 50 and the 51st block, we want to add a new block. Then, how many number of disk accesses are required? We are assuming that there are enough free spaces, and we also assume that the new block that we want to insert is also in the memory. Okay. So, how many number of disk access will be required to insert as the question here? So, we know that now let's take in case of contiguous allocation. So, we know that in case of contiguous allocation, if 50, 51, 52, 100. This is 50 and this is 51. So if we want to insert someone in the middle, we need to find a room here. So this can be found by shifting all this 50 disks to one block to the right. So we have to move all of this. So 100 has to go to 101. 99 will come to 100. 99 will come to 100. 98 will go to 99. Like that, 51 will go to 52, and the new one will come at 51. So we have um, we have to read first. We need to read 100, then write to 101. So every block we have two operation. One is we need to read this, and then we need to write to the new location. So for 100 we have to read and then write to 101. Same way 99 you read and then write to 100. This goes until 51, read and then write to 52. So total we have 50 plus 50, which is 100 operations here. And then 100 operations for this one. Then we have another one more. We have to also write the new block to 51. So we have 50 read, 50 write plus this new write, which is equal to 101 in case of contiguous allocation. Now, in case of linked allocation, how it will be is that so we can have it anywhere, right? It's not an issue. We don't need to have it continuously. Suppose this is 50 and this is 51, 52. Okay, 52. So this is how the link this will be. So now we need to read this. This is suppose this is the new block which wants to be inserted in the middle. So we need to read this, update the pointer here, then read it, update the pointer here. This will be done. So we have two reads here. We have two access, right? First we have to access, then we have to update the block pointer. Then we need to read the copy the new one and also update the pointer. So here we have only two accesses. Oh, sorry, completely sorry. This is with respect to changing the pointers, but to come to 50, yeah, we need to come all the way from 1 because it is a linked allocation, right? We cannot directly come to 50. So we have to go to 1, then 2, then 3, 4. We have to traverse through all the 50 and then 49 and then come here, 50. Then we have to change the this one in 50, then 51. So 50 access to reach 50 and then another 2 for changing the pointer. So 50 plus 2, I completely missed that. I just started off from 50. Now to reach 50, we need 50 accesses. Yeah. So this needs 52 accesses. So let's see one more question from file systems. So this is with respect to yeah, this question is with respect to indexed allocation. So here the question is consider a file of 16384 records. So all these questions are taken from Google. I mean, I get previous year gate questions. So each record is 32 bytes. Now key equal to 6 bytes and block pointer is of 10 bytes and one block is of 1024 bytes. Now the question is if secondary index is built on key field of the file and a multi-level index scheme is used. Secondary index, the number of first level and second level blocks is what the question is. Okay. So typically, we need to find how many blocks are needed in the first level indexing and also in the second level indexing. Okay. So content of the index table. So it's given that this key field is used as the secondary index. Okay. Secondary index is built on the key field. So size of index will be key plus block pointer size, which is equal to 6 plus 10, which is 16 bytes. So in the first level index, how it will be that we will have um, one entry for each record. So first level index for each record. So how many blocks? So how many records we have? So the number of records is records is 16384. Now size of one index entry will be 16. 16. Okay. So this many bytes will be there. Now how many blocks will be needed to fill these many bytes? It will be size of the blocks, which is equal to 256. So in the first level index, we will need 256 blocks actually. So here the idea is, so in the first level index, so this will be the second level index. We will have first leveling, sorry. Is my point. Then we will have the file. Okay, so here the logic is in the first level index, we will have one for each record, we will have a index entry. Index is created using the key size plus another 10 byte block pointer. So this is the so we will have the key size here, then block pointer. Block pointer will be used to point. Okay. So then how many ever records we have, that many into the size of the index entry. That many bytes we need for first level indexing. So that is this needed for first level indexing. This many bytes will be occupied in 256 block. Now we have 256 blocks in the first level. So the outer so we need one entry for each of these 256 blocks. So size of the entry is 16 bytes. So number of bytes required will be 256 into 16. And size of the block will be 1024. So we will need 4 blocks in the outer level. So or in the second level. So here the answer is so in the first level we need 256 blocks, and second level we need 4 blocks. Okay, second level index. So that is this question. Now we can go back to some old previous concepts covered in the earlier classes and just refresh couple of numericals through them. Okay, so let's start with semaphores, CPU scheduling. Okay, let's start with semaphores because I've not discussed any semaphore related problems earlier. Then we'll come back to CPU scheduling. Okay, let's start some semaphores. Counting semaphores. So I hope you will remember. So semaphores are majorly used for synchronization. It's a synchronization tool. Um, to synchronize the access of shared code or shared resources between multiple processes when they are accessing them in parallel. Okay, so we have two types of semaphores we had learned. One is counting semaphore and the other is binary semaphore. So with binary semaphore, it will take value 0 or 1. And so only if you are using binary semaphore at a given point of time, only one process will be accessing that particular critical section. Whereas in counting semaphore, based on the count value initialized, that many number of processes can enter the critical section. So here the question is initial value of counting semaphore is 10. Following operation completed on the semaphore in order 5P operation, 20P operation, 2V operation, 18P operation, 5V, 10P, and 1V. Question is what is the final value of the semaphore? What is the value of the semaphore is the question. After this execution. So we know P is like waiting. So we decrement. P is nothing but the wait operation. So we decrement the counter by 1. Whereas V is the signal operation. which means someone have exited the critical section. So it is incremented by 1. So now it is given that the initial value of semaphore is 10. And after that, 5 P operations are done. So every P operation is a -1. So 5 into -1 plus 20 P operations, which is again 20 into -1 plus 2 into +1, its increment, plus 18 into -1 plus 5 into 1, 10 into -1 plus 1. So the value was 10 plus, sorry, 10 minus 5 minus 20 plus 2 minus 18 plus 5 minus 10 plus 1, which is equal to minus 35. Okay, so after this many operation, the value of the semaphore will be minus 35. Okay, so and one more problem on same line. Consider a non-negative counting semaphore. Semaphore S, and during execution, NTP and 12 V operations are issued. So what is the value of S? So obviously, so let's take that. No, sorry, this is not a value of S. So what should be the SB initialized such that at least one process remain waiting for the log. Okay. So in case of counting semaphore, if the, for example, if I have four, if I initialize the counting semaphore value as 4, which implies that it can go down to 3, 2, 1, 0, right? 4 4 process can enter. So if I want only 3 process to enter, the value, it's not 0, it's still it's until it becomes -1. Okay, yeah, it's for counting semaphore, right? Yeah, so still it becomes -1. So here the question is, what should be the value of S initialized such that one of the process will be in the waiting state. So after this, so let's assume that so the value of X has to be uh, such that if we do the 20P and 12V operation, it will be 20 into -1 plus 12 into 1, which is -20 plus 12. So which means oh, sorry, it is one second. Yeah. So for counting semaphores, if one process needs to be in the waiting state, it has to be the final value has to be -1. So minus, we are starting with value of x equal to, we are assuming that the value of semaphore s is x. So on x, we are doing 20 p operations. So x plus 20 into -1 plus 12 into 1, which is x plus if we assume it to be 0, okay. If we are assuming it to be -1, then it becomes, okay, sorry, x plus 12 equal to 20 minus 1, which is equal to 7. So the value of x has to be, if we initialize the value of x as 7, then one of the process will go into, will be in the waiting state. So let's see if that works or not. So assume, let us take 7. So, and let's assume that first all the V operations happens. So 7 plus 12 is 19. And now when we try to do 20 V operations, we cannot decrement, right? Since the counting value, the value of counting semaphore is 19, only 19 processes will be able to enter the critical section. The 20th process will be in the waiting. Okay, so this is the formula. So if one has to be in the waiting, if no one has to be waiting, like if we want all the process to enter, then we can put it as 0. What should be the value of x if all of them enter? Then this will be 0. So it will be x plus 12 minus 20, which will be 8. But if we want one process to be waiting, then it is -1. If we want two of them to be waiting, then it will be -2. And then accordingly, the value of x will change. Hope it is clear. We will see another question on binary semaphore. So we have a, yeah. So the question is, program consists of we have three concurrent process and three binary semaphores. So the semaphores S0 equal to 1, S1 equal to 0, and S2 equal to 0. So they are initialized to 1, 0, and 0. And the process is the P0 is executing the P0 is executing the following code while true wait on S0. After that, it will print 0. After that, it will release S1, and again it will release S2. So while true. Okay. So this is the code of P0. P1 execute the code. It will wait for S1. Once it enter, it gets the lock. It will release S0. And P2 has the code. It will wait for S2. And once it gets the lock, it will release S0. So now the question is, how many times does the above program will pay maximum? How many times 0 will be printed? Okay, how many times P0 will print 0? So now let's see one by one. So when we have the value of S0 initialized to 1, S1 as 0 and S2 as 0. So when P1 tries to enter the critical section, wait on S1 will be waiting because S1 is 0. It will be looping here. Same way P2 will be looping here because S2 is 0. Until S1 and S2 becomes 1, they will not enter. Now wait on S0. On P0, it is wait on S0. S0 is 1. So it will go. It will go and print 0. 1 first time. Okay. Now after printing, it will release S1. Okay. It will release S1. Once this release happen, this wait call will proceed. Wait call will succeed because release will increment the value of S1 to 1. So wait on S1 will succeed. So once wait on S1 succeeds, P1 will go and release S0. Okay, so P1 will go and release S0, and then S0, the value of S0 will become 1. After this release of S0, this weight of S0 decremented it to 0, which is now again, after which it is set to 1. Now this release of S0 by P1 will make this S0 equal to 1. Okay, now again P0 is calling release of S2. After release of S1, P0 is calling release of S2. Release of S2 will increment the value, will make S2 equal to 1. So then this wait will succeed. P2's wait will succeed. Matlab P2 will be able to enter into the critical session because the value of S2 becomes 1. So once it comes down, this release, it again calls release of S0. Okay, P2 will call release of S0. So what will happen? S0, the value of S0 is currently 1. It gets again incremented. For understanding purpose, let's assume that it gets incremented and S0 value becomes 2. Okay. So now after this release of S2 is done, it's a while true, right? So now P0 will again do a wait on S0. So wait on S0 will succeed now because value of S0 is greater than 0. So again, it will enter here. Print of 0 will happen. Then again it will release S1. So S1 will become 1. S2 will become 1. Okay. But P1 and P2 does not have any while loop. Okay. So this is just a single iteration. Only one iteration. So it does the wait, then it release and exit. P2 will wait, release and exit. Okay. So though P0 makes the release the lock, make the value 1. P1 and P2 is no more executing. Okay. So this release of S0 from P1 and P2 will not happen. Now again, P naught will go to the while loop, while true. So here again, weight of S naught. So S naught value is 1 now. It is again because it had gone to 2, right? So it got decremented once. Now again, one more time, P naught will be able to enter the critical section because value of S naught is still greater than 1. So now again, it will reach here and it will print 0. So this program will print the value of 0 3 times. Nice. So that was one. Another question was, yeah, suppose we have a process P. Process Q. Process P have a while loop. While of 1. Okay. W. Print 0. 0. Then we have X. Again, while 1. We not also have similar code while 1. It has a Y, then print 1, again print 1, Y, Z, and followed by this. Okay. Now we have two semaphores, S and T. Now we want to synchronize the execution of P and Q such that we want the output to print as 1 1 sorry 0 0 1 1 0 0 1 1 0 0 1 1. So if we want to print the string in this pattern, what should be the synchronization statement inserted at W, X, Y, and Z? W, X, Y, and Z. So this is the question. Okay, the semaphore given us two semaphores, S and T, two binary semaphores, S and T, such that it will print. So if you see the pattern, we can observe that once you enter, after whatever we write at W, once we enter, 2 times 0 will be printing. And only after 0 is printed, 1 should print. And then after 1, 0 should print. So then 1 should print. So we should enter the critical session of P, then Q, P, Q, P, Q. In whichever order the processes get scheduled, irrespective of that, the critical section should be entered in the order P, Q, P, Q, P, Q. Only then we can get this pattern printed. So one way is, so we know first P has to enter, and at that time Q should not enter even if Q gets scheduled or okay. So if P has to enter initially, we have to have the value, suppose S and P. Let's initialize the value of S equal to 1. Okay. Now, and let us tell P of S. Okay. Now, if we initialize the value of P also equal to 1 and write P of P, then we will not be able to ensure this strict pattern because based on whoever gets scheduled, the print will come. So we have to ensure that the value of t becomes 1 only after, only at this point, that is only when 0 is printed. Only after that t should be becoming 1, so that only then q should enter the critical section. So we have to make sure that we initialize the value of t to 0 and s to 1, and then, like in the previous example we saw, right, this guy entered, he's waiting here. Now when it is released, this guy is able to enter similar way. So p entered, q is waiting because t we initialized it to 0. Now after that, now if we call p of t here, okay, now if we call, sorry, not p of t, v of t. Now if we call v of t is nothing but increment or signal. Now if we call v of t here, this will succeed. So we already would have had 0 0 printed because this was a ps was already initialized to 1. So one round it will enter, 0 0 is printed, and we are signaling, which means that this will enter, 1 1 will print. Now what we have to do? Now we want to go back here, and this has to print. So which means we need to signal S here. Now Z, when we signal S here, it will go here, it will print. Again we signal here, from here. So in this manner, we will be able to achieve the this particular pattern. So at W, we have to wait for S, that is P of S. So we need this. So the key is initialization also. S equal to 1 and t equal to 0. If we initialize it t equal to 1 and s equal to 0, then the pattern will be, if we do it t equal to 1 and s equal to 0, then the pattern we will get will be 1 1 0 0 1 0 0, that way. Okay, so this is the idea here. So we can achieve this particular pattern uh, by synchronizing the processes. Yeah. Now let's go back to from static. We'll discuss more. We'll go to some paging questions. Paging related questions. Okay, consider a demand paging with LRU paging replacement, demand paging system, 4-page frame, initially all empty. LRU page replacement algorithm. Now the what is the page fault rate? The page references. Seven, 2, 7, 7, 2, 7, 2, 2, 5, 3, 4, 6, 7, 7, 1, 5, 6, 1. Okay, so it's told that initially all are empty. So initially 7 will be accessed. It will be a page fault. Then 2 will be accessed. It will be a page fault. Then again 7 will be accessed. We'll bring it to the front so that the least recent is always in the front. Okay, now 3 is not there, it's a page fault. Then 2 was already there, we bring it to the front. It's a page hit. Then 5. So currently all the 5 are full now. Page fault, but no replacement. Okay. Now again 3 has come. We'll bring it to the front. Now 4. So all the frames are full. So there is a page fault plus replacement. So we'll replace 7 with 4. Now when 6 comes, again we'll replace it with 2. Now 7, again we have to replace it with 5. Again 7, there is no page fault. Now when 1 comes, we have to replace 3 with 1. Again 5. So we have to replace 4 with 5. When 6 comes, we'll move it to the front so that it will be the recent. Now when 1 comes, again we move it to the front. Okay. So the total number of page fault was the initial 4, 1, 2, 3, 4. Then the replacements that we did. 5, 6, 7, 8. Okay. So 1, 2, 3, 4. 70, 70. Do it again, sorry. Something I missed. Let me see the 7, 1, 2, 3, 8. 15. I didn't miss anything. Okay, so initially we have 4 empty frames. So when 7 comes, it is a page fault. 2 comes, it's a page fault. Then again 7 is referred. We just bring it to the front. Then 3 is referred. It's a page fault. Then again 2 is referred. Just bring it to the front. Then 5 is referred. It's a page fault. Then we have 3. So just bring it to the front. Now 4, we have to replace 7 by 4. Now when 6 comes, it is again a page fault. The least recently used is 2. So we bring in 6 in place of 2. Now when 7 comes, we replace 5 with 7. Now again 7 is access, so it's already there. Now when 1 comes, again it's a replacement. Now 5 comes, it's again a replacement. Now 6 comes, it just move to the front. And then 1 comes, again just move to the front. So the number of page replacements are all the cross that I have in the writing. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we have 9 page fault. And total references are 50. So page fault rate is 9 by 15, which is equal to 0.6. So this is the page fault rate. Now let's see one more question from this area, paging area. So it's given that Page fault service time be 10 millisecond with average access time. Average memory access time as 20 nanosecond. Then page fault is generated every 10 power 6 memory access. What is estimated memory access time? Okay, so we know the formula, right? EAT, expected memory or estimated memory access time, is page fault rate. We can call it P, which is nothing but page fault rate into page fault service time plus memory access time. Effective access time. P is effective memory access time plus 1 minus P, which is nothing but hit or a page hit memory access time. Okay, so here P is equal to, it is told that page fault is generated every 10 power 6 memory accesses. So page P will be 1 by 10 power 6. So now let's substitute and find out EAT, which is 1 power 10 power 6 into page fault service time is 10 millisecond plus 20 nanosecond plus 1 minus 1 by 10 power 6 into 20 nanosecond, which is equal to 10 millisecond by 10 power 6 plus 20 by 10 power 6 plus 20 nanosecond minus 20 by 10 power 6. So this term gets cancelled off. So 10 millisecond is equal to 10 into 10 power 6. 10 into 10 power 6 nanosecond. This gets cancelled off, which is equal to 20 plus 10, 30 nanoseconds. Okay, so the answer here, effective memory access time is 30 nanoseconds. Now let's cover maybe one. We'll go to one disk scheduling problem. Okay, it's given that the disk drive has 5,000 cylinders numbered from 0 to 4999. It's currently serving 143. Previously request was previous request was 125. This IO before order is 86 1470. 913 1774 948 1509 1022 1750 Oh, it vanished. Can I do again? Yeah, let me write again. Something happens and the app always does not really try. One three zero. Okay. So question is, what is the total distance that the disk moves? Request. So for a scan scheduling. So in scan scheduling, what happens is it will start from 0. It will go all the way up to the end 1499. Then it will come back to 0. On the way it will be serving request. On this way also it will be serving request. Again it go to 1499. Sorry, 4999 will be serving the request. Then again it will keep. So this is how the scan algorithm works. Okay. So now it is given that disk is at 143. Okay. So so at the right of the disk we have so let's just arrange it in this order, increasing order. We have 86 as the smallest. After that we have 130. Then we have 913. We have 948. And then 1022. I'm just arranging it in the increasing order. 1470. Then 1509. 1774. 1, 2, 3, 4, 5, 6, 7, 8. 3, 4, 5, 6, 7, 8, 9. I missed something. 86, 130. 86, 130. 913. 948. 1022. 1470. 1509. Okay, 1750. 1750 and 1774. Okay. So now, but the header is currently at 143. So it's here 143. Okay, and it was told that earlier it was at 125. So that information is given us to understand whether the arm is moving to the right or to the left. So if only 143 is given, we can assume that okay, it is in the reverse direction, and then we can tell that after 143, 130, 86 will be serviced. But since it's already given that the previous one was 125 and the current head is at 143, it implies that this is the direction in which the arm is moving. Okay. So, the next disk that will be accessed will be 913. Okay. So, from after 143, 913 will be accessed. So, the number of movements will be we have 86, 130, we have 143, 913, 948, 1022, 1470, 1509, 1750, and 1774. So from 143 to from 143 it will go to 193. Then it will go to 9. From there it will go to 948. So actually it just goes all the way till 1499. Say 4999. On the way it will serve all these requests. 1022 will be served. Then 1470, 1509, 1750, 774. And it will also go here. Okay. Then in the reverse direction, it will serve 130 and 86. So to compute the number of head movements, you can go it in this way. One way is like one by one, find out the movements. 143 plus 948 minus 913 plus 1022 minus 948. Like this you can do. Or another, let me write it fully. 1022 minus 948 plus 1470 minus 1022 plus, so now from here to here, that is 1509 minus 1470, then this line which is 1750 minus 1509, then this which is 1774 minus 1750 plus in the stretch 4449 minus 1750, sorry, not 1774, then the stretch which is 4999 minus 130 plus the stretch which is 130 minus 86. Okay, we can individually find all these numbers. Okay, but this is not actually required. So we know it's just traversing all the way till 4999. So it is, so this whole statement till this one, till this, from here to here is equivalent of 4449 minus 143 plus this 2. This 2 is equivalent of 4449 minus 140. Sorry, 86. Which is equal to 48. So sorry. This is 4999. How did it turn out to be 4449? Okay, so 4856 plus 4913, which is equal to 9769. So this is the number of head moments needed for this particular axis pattern. Okay. Yeah, now let's go to the page questions. So let's see some page table question. So, okay, and some questions from the page table memory byte, etc. So the question is calculate size of memory if its address consists of 22 bits and memory is 4-byte addressable. Okay. So what is being asked is size of the memory if its address consists of 22 bytes. Okay. So to do all these paging related problems, this concept of bit that manipulation needs to be very clear. So if we have 22 bits, it implies that we can have 2 power 22. We can address 2 power 22 different locations, right? For example, if let's take the simple example of 2 bits. 2 bits. With 2 bits, we can represent 0001, 1011. This is 0, this is 1, this is 2. In binary, okay, this is 3. So with 2 bits, we were able to represent 4 different numbers, 0, 1, 2, 3. If we make it 3 bits, it is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1. This is decimal 0, 3, 4, 5, 6, 7, which is again 8 values, 8 different values. So 2 power 3. So we represent 2 power 3 different values here. Okay. So that is the concept. So if we have n bits, it implies 2 power n different values. So if we are given that we have 22 bits in the address, which implies that this can have 2 power 22 different locations. It can address 2 power 22 different locations. Okay. That is if it is byte addressable. So that it implies that byte addressable, if this is 1 byte, 2, this is 1, 2, 3, 4. If each of this is a byte. Okay. Then byte addressable means this particular byte will have an address 0. This byte will have an address 1. This will have address 2. So all the bytes will have different address. But in the question it is given 4 byte addressable, which implies that 4 bytes together will have one address. So it will become, in case of 4 byte addressable, so this is 4 byte. This will have an address 0. The next 4 byte, this one. This will have address 1. Which in case of, what to say, byte addressable, this would have consumed 8 addresses. But since it is 4 byte address, we are consuming only 2 of it. So this is the difference between byte addressable. When we say byte addressable, this is what it means. Okay, 4 bytes is addressed using a single location. So now that we can have 2 power 22 different locations, and each location comprise of 4 bytes. So the total size of the memory will thus be 2 power 22 into 4, which is 2 power 22 into 2 power 2. So which is 2 power 24. Again 2 power 20 into 2 power 4, which is 16 MB. 2 power 10, we call it as kilo. 2 power 20, we mention is as mega. 2 power 30, we call it as giga. Okay. So it is 16 MB. Let's see another question. Consider a system with byte addressable memory. So byte addressable memory is this one. 32-bit, it's given that 32-bit logical addresses, 4 kilobyte page size, page table entries are of 8 bytes long. So what is the size of the page table in the system? So this is the question. Okay, so it is given that we have a 32-bit logical address space. So let's find out how much is the offset or a displacement and how much is the page bits. Okay, so it is given that we have 4 kilobyte page size. 4 kilobytes means 2 power 2 into 2 power 10, which is 2 power 12, right? So this is the size of the page. So this page, so this is byte addressable also. So each byte in the page can be represented using 12 bits. So 12 bits are sufficient to represent 2 power 12 different bytes. So the displacement within the page is can be represented using 12 bits. So the displacement or the offset is 12 bits. Now it's given that total it is 32. So 32 minus 12, which is equal to 20. Okay, so which implies that we have 20 bytes for representing the page number. 20 bits for the page number. which implies we can have 2 power 20 different, we can address 2 power 20 different pages, right? Now, if we can address 2 power 20 different page and each page table entry is of size 8 bytes, what will be the size of the page table? So what is page table? Page table is nothing but these are page table entry, right? This is one entry. This is 8 byte. This is another entry which is 8 byte. This is another entry which is 8 byte, right? We have 1, 2, 3 such 2 power 20 entries. 2 power 20 entries and each entry of 8 bytes wide. So total what will be? So this whole thing is the page table. The number of entries into, so this is like length into breadth, you can say. In a simple way, like how many we have here into what is the size of this. So n into like length into breadth or b into h kind of. Okay, so it is nothing but how many entries are there? We have 2 power 20 entries and each entry is of size 8 bytes. 8. So which is 2 power 20 into 2 power 3 which is equal to 2 power which is equal to 8 MB. 2 power 20 becomes megabytes. So it is 8 MB. So the size of the page table is 8 MB. Okay. So now let's see maybe a shortest. Now go back to CPU scheduling and try finding the turnaround time of one of the systems. So let's take the example of the shortest remaining time first, which is a preemptive algorithm. Okay, CPU scheduling. So shortest remaining time first, what it does is it's a preemptive version of shortest job first. Shortest job first will always schedule the shortest job available in the ready queue. But it's a non-preemptive one. So if a process starts and for example, if we have a process like we have a process P1 running, which is whose burst size is 5 units. It's currently running, and if another process P2 comes with burst size of 2 units, P1 will not be preempted. P1 will run to completion, then P2 will be scheduled. That is the shortest job first work. There won't be any preemption. Whereas in shortest remaining time job first, we have what is known as preemption. So every time a new process comes, it will check whether this new process burst time is less than the currently executing one's remaining time. So, for example, if it will check every time a process comes, it will check if the newly arrived process time burst time is less than the currently executing one's remaining time. If yes, it will preempt the current one and schedule the new one. At any given point of time, it will keep checking whenever a process comes, which one is smallest, and then it will schedule that. For example, if we have P1 and P2, arrival time is at 0 and 1, and this burst time is 4 and 2. So initially only P1 is there. P1 will start execution. But now at 1, when P2 comes in, it will check what is the remaining time of P1. Remaining time of P1 is 4 minus 1, that is 3. And the burst time of P2 was 2. So P2 was having smaller time. So P2 will be scheduled. P2 will be scheduled for completion, and then P1 will be again scheduled back. So this is the concept of shortest remaining time first. So P2 will run for 2, and then it will run for its completion. Okay. Let's take some example. So we have process We have remaining time. Sorry, not remaining time. First time. Arrival time. We have first time. We have P1. Arrival time P1, P2, P3, P4, P5. Yeah. The arrival time is 3, 1, 4, 0, 2. And burst time is 1, 4, 2, 6, and 3. Now let's draw the Gantt chart. So first arrival time 0. So P4. So we will first start with P4. 0, P4. The next arrival time is 1. Okay. So when P2 comes at 1. Remaining time of P4 will be 5, right? 6 minus 1, which is 5. But P2 has 4. So P2 will be scheduled. P4 will execute for 1 unit of time and then P2 will be scheduled. Okay. Now after P2, P2 will execute. P2 will execute for now at 2. That is one more unit. P2 will execute and see at 2, P5 will come. Okay. Now P2 have executed for 1 unit of time. So what is the remaining time of P2? 4 minus 1, 3. And P5 have come. The remaining time of P5 is also 3. So there won't be any preemption. So P2 will continue for one more time unit. Now 3. At 3, P1 will come. Okay. So what will be the remaining time of P2 at time unit 3? P2 would have executed 2 units. So 4 minus 2, 2 is the remaining time. Okay. Now P1 is having 1, P2 is having 2 remaining. So P2 will be preempted. P2 have executed for 2 time units. This is 1 unit. 1 plus 2, 3. Now P1 will be scheduled. P1 will execute for 1 time unit and it will complete. After P1 completes, P3 have come, right? Now P3 is also there. Now this is complete. Now these are the people in the queue. We have 1, 2 here. We have another 2, 5 and 3. So let's schedule P2. Let's bring it to completion. P2. Then followed by we will schedule P3. Then we will schedule P5. 3 units. 8 plus 3, 11. Then we will schedule the next 5 units of P4. Which is 60. Okay. Now, let us, what the question also asked for. No, I didn't mention that. Average, yeah, the question is actually find the average waiting time and turnaround. Okay. So we have this formula for turnaround time equal to exit time minus arrival time and waiting time equal to turnaround time minus burst time. Now let's do this Again, P1, P2, P3, P4, P5. Let's compute the exit time. Exit time, turnaround time, and waiting time. So exit time of P1 is, where is P1? P1 is getting over at 4. P2, let's start from this direction. Then we can see where P4 is getting over at 16. P5 is getting over at 11. P3 is getting over at 8. P2 at 6. So turnaround time is exit time minus arrival time. So for P1, the exit time is 4 and the arrival time is 3. So 4 minus 3, 1. For P2, 6 minus 1, which is 5. And for P3, it is 8 minus 4, 4. 16 minus 0, 16. And 11 minus 2, which is 9. Okay. So now waiting time is nothing but turnaround time minus burst time. So for P1, the turnaround time is 1 and its burst time is 1. So 1 minus 1 equal to 0. So P2, it is turnaround time 5, 5 minus 4, 1. P3, it is 4 minus 2, 2. P4, it is 16 minus 6, 10. And P5, it is 9 minus 3, which is equal to 6. Now average turnaround time equal to 1 plus 5 plus 4 plus 16 plus 9 divided by 5, which is equal to 35 by 5, which is 7. Now average waiting time equal to 0 plus 1 plus 2 plus 10 plus 6 by 5. That is 19 by 5, which is 3.8 units. This is how we compute the turnaround time and the average waiting time. We will see one more question from same SRTF because it's little tricky when there is a preemption coming in. It's slightly tricky. So let's do this one more problem. This is arrival time and bus time. P1, P2, P3, P4, P5, and P6. Arrival time is 0, 1, 2, 3, 4, 5. Bus time is 7, 5, 3, 1, 2, 1. So find the average turnaround time and waiting time. That is the question. So let's start from 0. So at arrival time 0, we have P1. P1 is executing for 1 unit, and after that P2 will come at time 1. So at time 1, P2 will come and then it will see, okay, 7 minus 1, it is 6 is remaining. It is having only 5, so P2 will be scheduled. Now, again, after one more time unit, P2 will be having 4 units left. P3 have come. P3 has only 3, so P3 will be scheduled. Now, after P3, again after 1 unit, P4 comes. P3 is done with 1 unit. 2 is left, but P4 has only 1. So 1 is less than, so P4 gets scheduled. P4 will be completed. Now after that, P5 comes at time 4. So when we have P5 and P3, let's schedule P3. P3 goes to completion. P3 goes to completion at unit 5. P6 comes with 1. But P3 is also now left with 1 only. So P3 will continue till completion. So P3 will continue till completion. It will go to completion. After that, now we have all these in the queue. So now P6 have the minimum job time. So P6 will be scheduled. After that, we have P5. Then after that, we have P2. And after that, we have P1. P1, which is okay. Now let's compute the average exit time. P1, P2, P3, P4, P5, P6. So the exit time of P1 is 19. P1 is 19, P2 is 13. Its exit time is easy if we go this way. It's easy to find that way. P5 it is 9. P6 it is 7. P3 it is 6. P4 it is 4. Oh, it wrongly. P1 it is 19. P2 is 13. P5 is 9. P6 is 7. P3 is 6. P4 is 4. Okay. Now we need to find the turnaround time. Turnaround time is the exit time minus arrival time. So P1 came first. So 19. Then 13 minus 1, 12. 6 minus 2, 4. 4 minus 3, 1. 9 minus 4, 5. 7 minus 5. Now waiting time is turnaround time minus burst time. So burst time for P1 is 7. So 19 minus 7, which is 12. Then for P2, burst time is 5. So 12 minus 5 is 7. For P3, burst time is 3. So 3 minus sorry, 4 minus 3. It is 4. It is turnaround time minus burst time. 4 minus 3, which is 1. And for P4, it is 1 minus 1, which is 0. P5, it is 5 minus 2, which is 3. And P6 it is 2 minus 1, which is 1. So now average turnaround time is equal to 19 plus 12 plus 4 plus 1 plus 5 plus 2 divided by 6, which is equal to 43 by 6, which is 7.17. And average waiting time equal to 12 plus 7 plus 1 plus 3 plus 1 by 6. So, meter vector 24 by 6, which is 4. So, this is how we compute the average turnaround time and waiting time. Okay. So, that's from the CPU scheduling side. We'll see one more problem. Screen is visible. It's coming up. Yeah. Yeah, so now maybe we'll take one FCFS first come first serve example. So the question is again, let's see the Gantt chart. I think it's very easy. Just P2, P3, P4, and P5 arrival time 3, 5, 0, 5, and 4. Burst time 4, 3, 2, 1, 3. So the Gantt chart will be first P3 have come. P3 will execute. So in first come first serve, it's a non-preemptive scheduling algorithm. So whichever process starts executing, it will complete it. So P3 will execute for 2 units of time. So at 2 units, nobody is there. So it's actually free. At 3, P1 have come. P1 will execute for 4 units. 3 plus 4, 7. Now, after 3, P5 have come. P5 will execute for 3. 7 plus 3, 10. Then who have come? P4 and P2. So we'll in this order if we take, let's put P2. P2 will execute followed by P4. So P2 will execute for 3, 13, and then P4 will execute for another 1 unit, which is 14. So when we come up with the Gantt chart, then we can easily find out the turnaround and the other time, because we have this values here, right? We have the exit. Okay, so once we know the exit time of P4, it is 14. Um, yeah, P4 it is 14. P2 it is 13. P5 is 10. Is 3 and 2. So once we know the exit time, it's easy to compute the turnaround time and the average waiting time. So let us have a one round robin example also. Probably we can quickly take and then wind up the session. So P1, P2, P3, P4, P5, and P6. So here the arrival time is 0, 1, 2, 3, 4, and 5. Okay, the burst time is 4, 5, 2, 1, 6, and 3. So if we round robin, I think you are aware, right? So there will be a time quantum. So here the time quantum given us 2 units. So every process will be given that many time units in a round robin fashion. Okay, so in this, so now here if you consider the arrival in P1, P2, P3, P4, so first P1 will be given 2 units, then P2, then P3, P4, P5, and P6. Then again we go back to P1. So in between, if any process completes, it's go out of the queue. Otherwise, until its execution is not done, it will be given in a round fashion. Okay, 2 quarters will, quantum units will be given. 2 time quarter will be. So P1 is coming at 0. It's this is 2. So it will execute for 2 time units. So now what is left is 2. By then P1 have come. P1 will execute. It will execute for 2. It will be left with 3. Let me wrap this up. Okay, now P1 is done. By then P3 is also come. P3 is also available. 2 units will be done. 6. It's now left with 0. So this is done. Now P4 will come. P4 will need only 1. So 6, 7. It will be done. Now P5 will use 2 units. So it will be now left with 4. 9. Now P6 will come. It will use 2 units. It will be left with 1. So 9 plus 2, 11. Now again, we will go back to this cycle. We'll go back to, from here, we'll again go back here. So P1 is now left with 2. So P1. So 11 plus 2, 13. Then P2. So this will be completed. Here, this will again go. 1 will be left. So P2 will execute. Now this is done. This is done. This will execute for 2 units. P5, 17. It will be left with 2. After that, this will be completed. P6 will execute for 1 unit, which is 18. Now this will be completed. P2, 19. And then this will be completed. P5, 21. Okay. So from this Gantt chart, we have the exit time of each process. So we know what is the exit time of P1. P1 is exiting at 13. P2 is exiting in this direction if it's easier. P2 is exiting at 19. P3 is exiting at 6. The first occurrence from the right will give you the exit time. P7, P5, 21, and P6, 18. So now from the exit time, we can find the turnaround time using the formula. Exit time minus arrival time is the turnaround time. Then from the turnaround time, we can compute waiting time by the formula turnaround time minus burst size is the waiting time. So then we can do the average. Yeah. So this is the probably I'll close the session with this. So any doubts, you can put it in the chat or you can unmute yourself and talk. Otherwise, if no doubts, we can wind up the session for today. Okay, thank you. Thank you for joining me. Thank you. Bye.